Hey guys, this is a video on more limits, and we're talking properties of limits this time. So I'm going to try to do this quicker because there's like a million properties of limits. Okay, so I just want to show you what I mean when I say properties. So there's like, we have exponent laws and laws of logs and stuff like that. So it makes it easier to evaluate them. We kind of have those properties of limits too. So for example, if I was going to evaluate the limit I'm stealing this from your textbook. So I'm just using your textbook, section 1.5, to go through this. So if you want to find the limit of a polynomial, like 3x squared plus 4x minus 1 as x approaches 2. There's a couple ways you can do this. So you can sub in 2 to your polynomial to see what it would approach. So like actually sub in. So 2 squared is 4, 4 times 3 is 12. Plus 4 times 2 is 8, so 12 plus 8 is 20, minus 1 is 19. So we know that that limit would approach 19. Okay, that was easy. You could also use properties of limits to evaluate it by splitting it up. So it actually works the same way if you wanted to evaluate it like this. You could say that that actually equals the limit as x approaches 2 of 3x squared plus the limit as x approaches 2 of 4x minus the limit as x approaches 2 of 1. So I can actually split up those three terms and find the limit of each term and then add or subtract them. So that's a property of limits. So for example, if I subbed 2 in, 2 squared is 4, 4 times 3 is 12, so that would equal 12. If I sub 2 in here, that would be 8. And the limit as x approaches 2 of 1 would still be 1. Oop, that's supposed to be a minus. So it would still equal 19. So, yeah, I mean, that's just one of the properties. And I just want to point this out again, like I did in the last video. If f of x is a polynomial function or a continuous function, then we always know that the limit as x approaches a of f of x is going to be equal to the value f of a. I said that in the last video too, and it's in the first video. So it's just emphasizing that if you have a continuous function, a polynomial is a continuous function, then you know that the limit of it is going to be equal to the y value at that x value. Okay, so let's just sum up some limit properties. I'm going to say them all. You can just copy them down into your book, and some of them you'll never use because they're so obvious, and other ones maybe you will use. So this is your huge list of limit properties. There's 9 of them. This is a boring section of the video. Sorry, it's maybe all boring, but anyways. Okay, property number 1 is a constant. So we say that the limit as x approaches a of a constant is equal to a constant, equal to that constant. So like that's like this example. So the limit as x approaches 2 of 1 is still going to be 1. Okay, so that's okay. I'm just going to write in brackets. That's a constant. Okay, second limit property. The limit as x approaches a of x is going to be equal to a. So that's just saying the limit of x as x approaches a is obviously equal to a. So, yeah, that's a good obvious one. Because that's just saying it's equal to whatever your x value is. Okay, question 3. Or property 3. So this is the one I just showed above, the adding and subtracting one. So the limit as x approaches a of something like two functions like f of x plus g of x can be split up into the sum of the limits. So the limit as x approaches a of f of x plus the limit as x approaches a of g of x. So if you have something all together, you can actually break it up and find the limit of each function. So if you have like, what is the limit of a sum? You can break it up into the sum of the limits. Okay, property number 4. It's the same exact property, but with subtraction. So should we write it again? I don't know. Could just put an add or subtract sign up above. I'm just going to write it again so you know. Works for adding and subtracting. Okay. G of x. Cool. We're working our way. Nearly halfway. 5. This one is with a constant. It's kind of obvious. So the limit as x approaches a of a function that's like got a constant multiplied by a function, you can actually toss that constant out front and just find the limit of the function without the constant and multiply it after. That makes sense? Okay. It makes sense because of rule number 1. The limit of the constant is just going to be the constant anyways. Okay, number 6 is a product one. So product and quotients work the same way as addition and subtraction. So the limit as x approaches a. So say you had a function f of x times g of x, and you want to find the limit of that. You can break it up, and you can actually find the limit as x approaches a of f of x, and then multiply that by the limit as x approaches a of g of x. So it doesn't really matter what order you do them in, as long as you find the limit of each and multiply it after, or find the limit, multiply them together first and then find the limit. And the same works for quotients. So the limit as x approaches a of f of x divided by g of x is equal to the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. And that is provided that the limit as x approaches a of g of x does not equal 0. Okay, otherwise we'd have a denominator of 0. Okay, so question A is with an exponent. So the limit as x approaches a of a function to the power of n, whatever n is just some number. So if you have a function with an exponent in it, then you could actually find the limit as x approaches a of that function and then put it to the power of n. So n is a rational number. Okay, and then finally, the last property, number 9, is with square roots. And that one says the limit as x approaches a of n root f of x can be equal to, you can actually root it after. So you can actually find the limit as x approaches a of the function and then take the root after. Awesome. Provided that root exists, I guess. So provided this guy in here doesn't end up equaling a negative value, and then you can't. Okay. Awesome. So that's all of our properties. And you may or may not need them, but at least you have a giant list of them. Okay, so let's do just a couple of example questions. Okay, yes, let's use the limit properties to evaluate a quotient. Okay, so let's say we want to evaluate the limit as x approaches -1 of a quotient, like x squared minus 5x plus 2 divided by 2x cubed plus 3x plus 1. So I'm stealing these examples from your textbook. So we can actually take the limit of the top and the limit of the bottom. So we can actually take the limit as x approaches -1 of the whole top. So x squared minus 5x plus 2. And then we can take the limit as x approaches -1 of the whole bottom. And I'm going to, they're polynomial functions again, the top and bottom. So I'm actually just going to sub in -1 in the top and the bottom. And I will get 8 over -4, which is -2. Awesome. Okay, let's try one with the square root. Okay, so let's say we want to evaluate the limit as x approaches 5 of x squared divided by x minus 1. Okay, so according to property number 9, check it out. I can actually do the limit first and then square root after. Okay, so let's do it. So instead of like, well, I mean, it's really the same thing. Okay, anyways, so let's take the limit of the top as x approaches 5, and let's take the limit of the bottom as x approaches 5. I mean, it's really the same thing, so no big deal. Okay, so 5 squared is 25, and 5 minus 1 is 4, and then we're going to take the square root. I'm going to, since 25 divided by 4 is not really a nice number, I'm actually going to square root the top and then square root the bottom, because that's a property of radicals, so that would be 5 over 2. So, I mean, limit properties in these cases aren't groundbreaking. Okay, let's try kind of a crazy one that I just saw in your textbook. So what if you had, let me just see here. Ooh, I might save that for another video. I'm sorry, I just wanted to talk about limit properties in this one, which I think I covered. So yeah, these are your 9 limit properties, and these are like ways you can apply them. Sorry, I'm just seeing if there's any other good examples. I'm sorry that I didn't. Oh, let me just show you one more thing, because there's times when you actually can use limit properties, but it still doesn't help you. Okay, so let's take out this one. The limit as x approaches 2 of 5x over x minus 2. So regardless of what properties you use, like you could use the property where you take the limit of the top and bottom, you take the limit of each thing, regardless, this limit is not going to exist. So if I just subbed in 2 right now, I know the denominator is going to be 0, because 2 minus 2. But even if I decide to take the limit of the top function, so the limit as x approaches 2 of 5x, and then maybe I'll even split the bottom one into the limit as x approaches 2 of x minus the limit as x approaches 2 of negative 2. Oh, that'd be positive 2 since I put the minus sign there. Okay, so then I know the top would end up equaling 10. The limit of x as x approaches 2, that's another property. That value would just be 2. I think that's property number 2. Yeah. Property number 2. Minus, this is the constant property. That's just going to equal 2. So we get 10 over 0, which is undefined. So we would say that the limit as x approaches 2 of 5x over x minus 2 does not exist. So there's cases where that happens sometimes. And you always want to kind of evaluate, I'm going to get into this in the next video. Is there anything I can do to manipulate this at all? But there's nothing. There's no factoring. There's no rationalizing the denominator. Like, there's nothing we can do. That's the expression, and there's no limit that exists. And let's just take one, sorry, you can stop it here if you're bored, but let's just take one look at what the graph looks like. I should have left that. Okay, so y equals, I forget, 5x over x minus 2. 5x divided by x minus 2. So the reason this function doesn't exist at 2, that's right where that an asymptote is. So that limit can't exist, because if you're approaching from the left, you can see that as you're approaching from the left, as you're approaching 2 from the left, you're getting closer and closer and closer and closer to like negative infinity. And over here, you're getting closer and closer and closer and closer to positive infinity. So the left and the right hand limits are not the same. Therefore, the limit can't exist. So sometimes it's nice to look at the graph so we can get a picture of what's going on. Okay, so that is properties of limits.